today I will talk a bit about our global illumination resampling algorithm with caustics. And for caustics, you can see an example on the left video, which are basically bundles of reflected or reflected light by highly specular materials. And this resampling algorithm basically works on very large scenes with many lights, and you can see a little example on the right side. But first off, what is ReSTIR, or why should we use resampling? So while we have hardware ray tracing since a few years, tracing rays is still very expensive. And for real-time frame rates, often only a couple of frames are actually possible. And this will often lead to noisy images, as you can see on the right side. And the question ReSTIR basically solves is, why should we start from scratch each time if we already found some good samples? And this is what ReSTIR does. It basically increases the effective sample count by reusing some samples from other pixels, from the neighborhood, or from the past. And ReSTIR was first introduced by Bitterly and colleagues to render millions of direct lights. And since then, it was basically expanded to every major global illumination algorithm, like path tracing. We've done finer gather photon mapping 2 years ago at EGSR in London, and also bidirectional path tracing. And for ReSTIR, there are also many, many, many more papers. But on this work, we will focus to improve the shortcomings of our previous algorithm. So now I will talk a bit about it, so to give you an idea how it works, or how it worked. So for our ReSTIR-FG, we use two types of samples. One are finite gather samples, where first photons are distributed from the light source, and then the camera distributes the ray and traces it until the first diffuse hit. And on these first diffuse hits, a finite gather ray is dispatched, which is basically a ray with an radiance estimate operation, where all photons are gathered in a radius. And these will lead to noisy path tracing-like images for the diffuse indirect illumination. And for resampling, we basically reconnect to samples from past or neighbor pixels. The second type of samples we have are caustic samples, where again photons are traced from the light source, and then we distribute ray from the camera until the first diffuse hit, and this time we evaluate the caustics directly using the radiance estimate, and also if the first hit was specular, we also collect the direct light photons. And this will cause photon blob-like noise, as you can see on the bottom middle picture. And for reuse, we basically reuse the radiance estimate samples from the last frame. But this had some problems. One of the problems was insufficient photon density. So for example, on very large scenes with many lights, we cannot trace enough photons in real time, and this will cause these correlations, as we have a few photons that are very bright. But also, we can't find any caustics, as the density is not high enough. Also, we assume that the first diffuse hit is always similar, which is not always be the case, especially on glass materials or rough specular materials. And this will cause noise because these samples are rejected. And also, we didn't verify any caustic samples, any photon samples, and this will cause lag for the photon samples if, for example, the glass moves. And we will address all these three problems with our new algorithm-guided ReSTIR-FG+. Yeah, first off, we will take care of the insufficient photon density, which will be taken care of by the guided path. And for that, we introduced real-time photon guiding. And to give you a basic idea what photon guiding does, it improves the photon density by tracing more photons to the, by distributing more photons to the more important regions. So for example, on the bottom right, you see now ReSTIR-FG without any guiding, and now with guiding using the same amount of photons. And our guiding uses histograms similar to Gridman and colleagues, and but we use two-level guiding for our real-time guiding. We first guide to the relevant light sources, and if a light source is relevant enough, we also do directional guiding. So first off, we need to actually record the contribution, and for that we start with a uniform distribution because we have, of course, no further knowledge of the scene composition. And to record any contribution, we use recording textures, where one for all light sources, where each cell represents a light source, and each light source also has a directional with discretized direction, where each cell is a discretized direction. Additionally, now every reservoir needs to store light information, so the light ID and the initial direction for a selected photon sample. And now for every reservoir, we basically record the contribution. As you can see here, we start with on this pixel grid, for example, and the first two didn't have any samples, but this one has one. And so we use the light index to add the contribution, and the contribution is basically the discretized final color for that reservoir. And we also do that for the initial direction. So after we've done that, we convert these recording textures into histograms, where now each cell contains a weight between 0 and 1, and the sum of the whole histogram is 1. And because we also don't want to start from scratch for our guiding, we use the temporal information from the previous frame and use an exponential moving average to update the current histogram. And exponential moving average is very well suited for real time, as it adapts very quickly to changes. These histograms will then be converted into our guiding maps, and a guiding map cell basically contains the number of photons we want to trace for that cell. So now we distribute our photons we want to trace this frame to the guiding maps. And before we use the histograms, we reserve some photons per cell. And it is very important that each cell gets, or each light gets at least one photon, because if a cell would reach 0, we would never again find that light, and this would be very, very bad for a real-time context, as the light would basically be out forever. The remaining photons are then distributed using the histogram. And for each light cell, we then check if this cell is relevant enough and distributes enough photons to justify using directional guiding. And if it does, we do the same procedure. So first reserve at least one photon for each cell and distribute the remaining photons using the histograms. So now to create an actual photon sample with these guiding maps, this is pretty simple. We generate a quad tree using mid-maps, so just the sum of 4 pixels for the next level, and then use a unique shader dispatch index to create a sample. And this will basically traverse the quad tree until it lands at a light, and this light will be selected. And again, we need to check if this light uses directional guiding. If it would not use directional guiding, we would use random direction at this point. But if it uses directional guiding, we continue traversal until we reach the bottom of the directional guiding map, and then we also apply a subpixel jitter so we don't get any discretization artifacts. Yep, and this basically takes care of the photon density problem. You can now see no correlations at the wall, and also caustics are now present, using the same amount of photons in both cases. But for scenes with many lights, we can waste a bit memory if we store a directional guiding map for each light, and memory is currently expensive, so best not to do that. And actually, we don't actually need that many directional guiding maps, because only a couple of lights actually have enough photons to justify these. So for every light that actually uses the directional guiding maps, we assign a unique mapping index using an atomic counter, for example. And these indexes will map to the directional guiding resource. And now to actually update and create them, we need the information from the last frame, and we now basically have 2 cases. The first case is we didn't have any directional guiding information in the last frame, and in this case we initialize the directional guiding map as uniform. And the second case is if we had one, Then we use the recording data and also then the histogram from that index in the last frame to create and update the current one. And here's a little example. On the bottom left, you can see the dynamic directional resources loading in and out. On the bottom right, you see an atlas for the whole scene. Okay, this covers the guiding part, and next up to the improved resampling algorithm, which we improved using other techniques that came out in the last 2 years. First off, we use 2 types of samples in our improved resampling algorithms, but they are now a bit different. But we first start again by tracing the photons from the light scene, and this can, of course, now be happen with guiding. And we have 2 cases. If the first camera hit hits a diffuse surface, we do a normal finite gas array, like in the normal ReSTFG. But if we hit a specular surface, we have now 3 kinds of parts that can happen. So first off, we do radiance estimate for the caustic photons, then a next event estimation for direct light, and finite gas array for the indirect light. And we use resampling to select one of these paths. The second part are the directly visible caustic samples, and these are generated by back projecting each caustic into the camera, similar to what bidirectional ReSTIR does. To reuse these parts, we now use shift mapping instead of simple reconnecting. So for example, if the camera moves, if we hit a diffuse surface, we can actually just reconnect. And if we hit a specular surface, we need to retrace these paths by copying the random numbers. And then we need to replay the decision we made for the path. So for example, if we had a caustic photon, we need to verify if this is still in the radius. If we did next event estimation, we need to reconnect. And if we did a finite gas array, we need to also reconnect to that sample. And this basically takes care of the specular materials. Now it can also happen that the photon paths are invalidated, as I've shown before. So for example, if now this glass sphere moves, we also need to retrace these photon paths. And this is again done by copying the random numbers. And for the caustic reservoirs, the samples are splattered back into the camera using reservoir splitting. And for the other paths will be taken care by the hybrid shift I've shown in the previous slides. And this takes care of the temporal lag for the caustics on the trade-off of a bit more noise. Now to some results. On the top left, you can see ReSTIR PT. On the top right, you can see our previous ReSTFG without guiding. Bottom left is guided ReSTFG, and bottom right is guided ReSTFG plus. You can see that ReSTIR PT creates some correlation artifacts on caustic paths because these have very high variance. But photon mapping handles these much better. For large scenes especially, ReSTFG has not enough photon density, so you don't see anything behind these glass, and our caustics are not visible, but our guided algorithms can handle this. And in terms of runtimes, our guided ReSTFG Plus is around the same as normal ReSTIR PT, and ReSTFG is a bit faster, but has the problems I mentioned before. And the guiding in itself is not actually that costly, as you can see in the difference between ReSTFG and guided ReSTFG. Yeah, to conclude, we presented a high-quality resampling algorithm for global illumination with caustics, and this is effective across a huge variety of scenes, ranging from large scenes with many lights to small scenes with a few lights, and now supports fully dynamic scenes. And I thank you very much for your attention.
Any questions from the audience over there?
Thank you for the talk. I have a question about the guiding map initial samples. So I remember that for light, you start from 8 samples, and for direction, 1 sample. And how do you find this number, like 8, 1? Why not like 9, 2? Is this number like a sweet point for most of cases, or there are some edge cases that you just ignore them?
This is actually just an example. You can use any amount, and we actually have an optimization which I forgot to talk about. So it's great you asked this question. So in the paper, we optimized a bit more, and we've done optimization based on camera distance to the light. So for lights that are near the camera, so they are most likely more relevant. They get assigned more initial photons, and lights that are further away get less photons. But they need at least 1, and that is the important part. But it can be any number you can allow in the budget. For our tests, I think we used on small scenes, we used 64. Was a good sweet spot, and for large scenes we use the dynamic.
Okay, thank you.
If there's moving light with your photon guiding approach and the moving average, do you get like additional lag? Because now you solve the lag with the camera that move, but if the light move and you still
that could happen. That it's a bit more noisy if light moves, but it should be able to handle this because the exponential average is really, really fast.
Okay.
So normal light movements are fine, or should be fine.
Thanks for the talk. It's very nice work. I'm just wondering because you implemented this in Falcor, if I understood correctly. Is that correct? You implemented this in Falcor, is that correct?
Yeah, I implemented.
So Falcor has these very, the best quality denoisers around, right? Did you ever turn on the denoiser? Because the question I have is, there's a certain level above which you have enough samples for the denoisers to work. Have you achieved that level?
Yeah, it's actually a bit tricky while this implementation exists, they're actually a bit tricky to implement, and this is huge work because you need to implement your whole algorithm around that you use denoising. We've done some tests, and it's always a bit mushy because the implementation is not really wide. But you should be able to denoise it because quality is much higher, and it's similar noise to normal ReSTIR algorithms. So if they can handle these, they should also be able to handle this one.
Hey, if I understand correctly, you're guiding the direction for the photons. What happens if you have a super large area light source? I mean, your caustic would obviously get very blurry, but do you run into trouble? Did you try a light source like that?
Yeah, we actually did try that. It's in the supplemental video. And what actually happens, it was a bit surprising for me as well, because I mentioned that you could just subdivide these large light sources and then you would have less of a problem. But this actually degraded the guiding quality a bit as if we would use one huge large area light instead. Probably because for this test we mostly tested small objects and relevant directions were similar enough in this case. But it still works.
Interesting, thanks.
All right, let's thank the speaker again one more time.